welcome to RF transceiver design course. We are at module 5. We are discussing about passive components and impedance matching. In last lecture we have seen the transmission line and we have discussed the special case of transmission line, that is a quarter wave transformer. Now in one of the important parameter of the transmission line is the transmission coefficient, that how much amount of power which is transmitted. So you can mention a transmission coefficient T, which is 1 plus gamma. So equal to 1 plus gamma, we already know Z1. So if this impedance is Z1, Z1 minus Z0 upon Z1 plus Z0, which is equal to 2 Z1 by Z1 plus Z0. So here you can write at Vz, where Z less than 0, you should consider the reflection coefficient gamma, and when Z greater than 0, that is a transmission coefficient T. So this T is often expressed in dB and described as a insertion loss. So the way we have considered the return loss will tell us that how much power is returned back, and insertion loss will tell us that how much is a loss happening when there is a how much power is transmitted. So insertion loss, that is a combination of minus 20 that is given by minus 20 log of T. So what is the ideal value of insertion loss? We want there is a no insertion loss, all the power will be transmitted. So the ideal value, so this gamma, when it is 0, this is equal to 1. So this is the ideal value, but in reality getting 1 is not difficult. So it is considered as a 0.9, as I told. If you consider the gamma, which is a 0.1, so that will have a the insertion loss will be in the range of 0.5 to 0.6 dB. So this is how these are the two important parameters: reflection coefficient and the transmission coefficient, and return loss and the insertion loss. Now we will see the Richter transformation. The why it is important to understand Richter transformation, because in many high frequency circuits, if you are going for millimeter wave or sub terahertz transceiver design, in that case you can realize the inductor or capacitor by just using a length of the transmission line. So we already know for short circuit your Zin is equal to JZ0 tan beta L, and your open circuit minus JZ0 cot beta L. So you can easily represent your Zin in terms of ZL, which is equal to J omega L, and ZC, which is equal to minus J by omega C. So now if we consider, if we fix the length of the line by lambda by 8, so if we consider the length of the line, which is LC by 8, then what will come? Beta into L, beta C into L will come as a pi by 4. So your 10 pi by 4 is equal to 1. So if you want to represent J omega C L, which is equal to J Z0 10 pi by 4, so it is nothing but J Z0. So you can easily find Z0, which is equal to omega C into L. So it is, you can realize the inductor value of Z0 by and if you want inductance of L, you can easily find the Z0. So for example, if you are representing the, if your omega C frequency is a 30 gigahertz, this is an example, and if your length, if your inductor that you want is a 1 nanohenry, if inductance that you want is 1 nanohenry, then your Z0, which is omega C into L, which will roughly come around 30 ohm. So if you make a transmission line which has a length of lambda by 8, that is lambda C by 8, and if your Z0 is a 30 ohm, then you can represent it as the inductance of 1 nanohenry. So this is by this way, by using a Richter transformation, you can realize 1 nanohenry of inductance just by a small length of line. Similarly, you can also represent the capacitance. So, the Z naught which is equal to 1 by omega c into C. So, whatever capacitance you want you can realize just by a open circuit. So, the difference in inductor you should use a short circuit line, and in capacitor you should use a open circuit line. So, here if we same thing is mentioned, I am not reading the same, but your Z naught is equal to omega c into L. So, and your in the case of capacitor your ZL which is equal to J by omega. So, here your ZL which is equal to J by omega c into C. So, your Z naught here is 1 by omega c into C as I mentioned in the last slide. So, it is important to remember that Richter transformation do not result in a perfect replacement of a lumped element. It is not, let us say you have a lumped inductor, you cannot completely replace the same. And the stubs, this is also called as the stubs, do not behave like capacitor and inductors, but you can use it only for certain frequency. So, instead the transformation is perfect, the impedance are equal, but only at one frequency. If your frequency or your bandwidth is wide, if it is changing, then there is a variation in the inductance. It is not the same inductance that you see, and we can use the Richter transformation to replace the inductors and capacitor of the design lumped element, and sometimes it is beneficial because on chip if even the inductor that we use a spiral inductor, it is at high frequency it is reducing the size and your requirement of picohenry or very less value of inductance you can easily realize by using the transmission line. So, and another thing is impedance is a periodic in nature. So, it will change periodically with the distance. So, there are two transmission line that is a widely used in the RF receiver design. One is a Stripline and then another is a Microstripline. So, what is a Stripline? So, Stripline there is a this is a substrate, and inside the substrate there is a conductor. So, on the substrate, so there is a substrate on which there is a top ground plane, on the bottom there is a ground plane, and in between there is a conductor line where the signal will travel. So, there is a electromagnetic wave which will travel. So, you can get the electric field which is mentioned by the thick line and the magnetic field which is mentioned by the dotted line. So, electric field will be from signal to ground, and around the electric field there is a magnetic field, and there is a TEM wave, transverse electromagnetic wave, which will transfer over the strip line. So, you can get Z naught if it is a lossless line L by C, beta, omega, and all this equation you can use for this strip line transmission line. Now, important thing is to find the Z naught, because in all the case if we have taken all the example of Richter transformation or the quarter wave transformation, what we want to realize is a certain value of Z naught. If you know the value of Z naught, you can identify the width, that is this width of the conductor. You already know the epsilon r, that is a relative permeability, and if you know the epsilon r of the material and if you know the thickness, so that is a thickness which is given by a B. So, thickness of the substrate, if you know, then you can write the equation, that is a Z naught B W E. So, this is a effective width plus 0.441 B. So, this you can consider W by B greater than 0.35, or for WB which is a less than 0.35. So, these formulas assume a strip with a 0 thickness and are quoted as being accurate to have a 1% of exact value. So, if you use this equation, you can find the value of width for your Z naught, which is let us say whatever Z naught you require. And you can use this all equation are came from the complex Maxwell equation analysis on and the transmission line. So, you can use a line calculator as well to find out the value of the width means effective width for considering the Z naught. Similarly, there is a microstrip line. So, the difference between microstrip line and strip line only one difference, that is there is a air at the top, at the bottom there is a ground plane and there is a conductor. So, in strip line top and bottom both there is a dielectric, but in this case there is a air and bottom there is a dielectric. So, in this you need to consider the effective epsilon r, which is a combination of the epsilon r plus the air epsilon r. So, effective relative dielectric constant, and that is a epsilon r combination of air. So, this is epsilon r plus 1 by 2 and epsilon r minus 1 by 2, and this is a equation to find the effective epsilon r. Only the difference is this, you can use the same formula that is a Z naught and to find the W by D, and this equation is taken from the reference. You can go to the reference if you are interested for the more in detail analysis for this strip line and microstrip line. So, these two are widely used transmission line in the on chip circuit also. So, how it can be used? We will take one example of the CMOS process. So, if it is a back-end line CMOS process where there are 9 metals. So, if there are M1 to M9 metal layers. So, how the CMOS process has? It has a multiple metal layers to connect the various components. Now, you can realize the microstrip line or strip line by using this metal stake. So, we can avoid the poly because it is more resistive. You can use the M1. So, just this M1 can be used as a this is M1. So, this is a ground plane, this is a M1 line. In between there are a substrate. So, up to metal 9 there are all the epsilon r. So, you need to find the epsilon r, means you need to combine the epsilon r of all the thickness. So, you know the epsilon r, that is the effective epsilon r, and you can consider, you can calculate the effective epsilon r of the complete stack, and then there is a metal 9. So, you can use a metal 9. So, this is a metal 9. So, you can easily realize. So, entire this is a substrate. So, you can realize the microstrip line by using the back end line of process by using a different metal layers. You can also get the strip line. Only the thing is, in the strip line and microstrip line there is a substrate above. So, in between any metal layer you can use, let us say metal 6, and above metal 8 and 9, means metal 9 is the ground, and below metal one of the metal will be ground. So, that will be used as a strip line. So, this is the way you can find out the Z naught on the, because you know the epsilon r, effective epsilon r, you know the breadth, the what is the breadth of the your substrate, then you can easily find, and you already know the Z naught that you want, then you can find the effective width of the transmission line. So, this is how the you can use a microstrip line or strip line on the CMOS process. It can be used in a bi-CMOS process also, where the multiple metal stakes are there, but only the important part is your metal 9 mostly is used because it has a more the conductor is a more wider compared to the other metal layers. So, now we will move to the, so we already have discussed the uh, most of the thing related to the transmission line. Now, based on the understanding of the transmission line, whenever you try to connect any component at high frequency on chip, or even you are designing a PCB for RF component measurement, you should keep in your mind the effect of transmission line, and if there is a mismatch you need to match the impedance. Otherwise what will happen, there is a more reflection and by using a reflection coefficient you can find out the how much amount of reflection will happen. By using the transmission line voltage and current equation you can also find the different phase at each stage. So, now another important aspect when you are designing the RF circuit, that is a two port parameter. So, you should also have an idea about the two port parameter, which are widely used in the microwave or millimeter wave or sub-terahertz circuits. You already know the Z matrix, Y matrix. So, this is also called impedance matrix, which will give you the impedance. So, V1 is equal to Z11 I1 plus Z12 I2, V2 which is equal to Z21 I1 plus Z22 I2. Y matrix, it is the inverse of Z, that is I1. So, here you should consider the current which is equal to Y11 V1 plus Y12 V2, and I2 which is Y21 V1 and Y22 V2. How to find the Z matrix? You all know it is very simple. If you want to find the Z matrix, you need to make your I2 current. So, in order to find the Z11 and Z21, you need to make I2 current 0. If you make I2 current 0, if you make it open circuit, then you can get a Z11 which is V1 by I1 and Z21 that is the V2 by I1. And if you make I1 is equal to 0, you can get the another two parameters. When you want to find the Y matrix, what you need to do is you need to short. So, you need to make V2 is equal to 0 and V1 is equal to 0 at in order to find the all the parameters. So, your Z parameter are inverse of the Y parameter. And similarly H matrix also is widely used. So, it is mostly used in active components because there is a gain is involved, that is V2 and V1 and I2 by I2 and I1, where so H12 and H21 will give you the gain, and you can find the H parameter by making V2 is equal to 0 and I1 is equal to 0. Another important parameter is the ABCD matrix, where ABCD matrix is important when you have more cascaded component, and you can easily just do the matrix multiplication and find the complete system parameters. So, your for S matrix, that is V1 which is equal to A I1 B V2, I1 which is equal to C I1 V2. So, in some of the cases if the current direction of current is different, then this might be negative sign will come here. So, these are the 4 parameters you already studied and you are using, but there are for RF transceiver design there is a special parameter, that is a S parameter that we need to consider. So, why S parameters? Everyone it will come in mind, but we have already these many parameters, why it is important to consider the S parameter. So, in the previous parameter what we have done, in order to get the Z or Y or ABCD or any other parameter, you required a total voltage and total current. Now, there is at high frequency it is very difficult and no equipment available which can measure the total voltage and total current. And in Z parameter and Y parameter what we have done, we have easily make open circuit and short circuit. It is very difficult to make open circuit and short circuit at very high frequency, it will start radiating. Now, instead of that you need to find out the parameter which do not require the open circuit and short circuit. The third important point is a active devices such as a transistor, because we are going to use active devices in order to make a amplifier or any other components that we have studied in the when we have discussed the receiver architecture. There are many components. If you want to make all the components, you need to use the active devices, and it will become unstable under open circuit or short circuit condition. So, that instability will lead to the there might be possibility that your device will not work well, or there is a burning will happen in your chip. So, you need to consider that you cannot easily open and short circuit and high frequency. Now, what is the solution? The solution is a S parameter. What exactly S parameter will do? S parameter will be defined based on the reflection, means how much voltage is reflected and how much voltage is transmitted, and there are always a match load is considered. So, if there is a N port network, so in the previous parameters we have considered only single port network. So, if there are 1 to N port, then you can write S parameter of N port network as a V1 minus to Vn minus by S11 S12. So, this is the complete N port S parameter. So, if you define the V minus in terms of S V plus, so you can find Sij which is equal to Vi minus by Vj plus, where Vk plus is equal to 0, where k is not equal to 0. So, if we have a 2 port, let us say if there are 2 port, and then you want to find the S parameter V1 minus V2 minus S11 S12 S21 S22 and V1 plus V2 plus. So, how to find the S parameter? In order to find the S parameter, you need to make V2 plus is equal to 0. So, how you can make a V2 plus is equal to 0? V2 plus is equal to 0 means there is a, let us say V1 plus is incident and V2 V1 minus is a reflected, V2 plus is incident from this side, this is port 1, this is port 2, and V2 minus which is a reflected. So, if you see from port 1 side, V2 plus is a reflected wave. How you can make a reflection 0? So, in order to make your reflection 0, we already have seen gamma which is equal to ZL minus Z0 by ZL plus Z0. So, if you make a ZL which is equal to Z0, so you will get a, so for ZL is equal to Z0, you will get a reflection coefficient is equal to 0. So, how you can make V2 plus is equal to 0? By making a reflection coefficient 0, and you connect the match load, that is a Z0 50 ohm impedance. You connect a match load at the output and find the voltage V1 plus V1 minus and V2 minus, and all the parameters can be find out. So, that is a big difference between the parameter that we have seen A, B, C, D, H, Z, Y. Here you are going to use a match load in order to find the S parameter. So, mostly this is a widely used equipment VNA, that is called vector network analyzer, and this is a 4 port vector network analyzer from previously it was called Agilent, now it is a Keysight, where you can have a you can find various S parameters. So, S parameter generally measure in a dB. So, y axis is a dB and x axis is a frequency. So, all the S parameter, so all the network parameter you can find by using a network analyzer. So, if you want to consider the generalized S parameters, so the difference between the previously we have just considered the voltage quantity, but in generalized S parameter it is a normalized with root 2 z naught. So, RMS value is considered, because you can directly, the square term is directly represented as a power, incident power and a reflected power. So, here A is a normalized incident voltage wave, which is given by V plus by square root 2 z naught, and B is a normalized reflected voltage wave, where B is equal to V minus square root 2 z naught. So, here A1 is a incident voltage, incident normalized voltage, B1 is a reflected normalized voltage at port 1 and here at port 2. So, if you consider Z naught is equal to 1, you can write V plus by root 2 and V minus by root 2. So, there are 4 important parameters. So, you can easily write B1 in terms of A1 and A2. So, B1 which is equal to S11 A1 plus S12 A2, B2 is equal to S21 A1 plus S22 A2. It can also represent in terms of matrix B1 and B2, then S11, S12, S21, S22, A1 and A2. So, what if we find a, if we want to find a S11, then we need to make A2 is equal to 0. So, S11 is nothing but B1 by A1, and this is the input reflection coefficient gamma in, which is very important parameter when we want to find the input matching. Then there is a S12, which is a B1 by A2, which is a reverse transmission coefficient, which will also provide the reverse isolation between port 2 and port 1. Then S21, which is B2 by A1, where A2 is equal to 0. This is mentioned as a forward transmission coefficient, and that is also mentioned as a gain when there is an active component, because B2 is the output and A1 is the input. So, output voltage by input will give you the gain. So, in many amplifier, mostly low noise amplifier and power amplifier, S21 is considered as a power gain. Now, S22, it is B2 by A2, A1 is equal to 0, it is output reflection coefficient gamma out. So, S11 will give you the input reflection coefficient, S21 will give you the power gain, S12 will give you the reverse isolation, and S22 is the output reflection coefficient. Your incident power you can easily write in terms of V plus I plus conjugate, that is V plus square by 2 z naught, and it can easily be written as a A1 square. And your reflected power is mentioned as a B1 square. So, your total power P, which is a combination of incident A1 square minus B1 square. So, based on the S parameter, you can also find out the incident power and reflected power. Now, another important consideration of the S parameter, that is if you shift the reference plane and if your line is lossless. So, I just want to give one example here, that if your antenna is lying at the very means high in the building, and if your base station is at the bottom, your power amplifier is connected at the bottom, and you need a transmission line which is connected from bottom to the top where antenna is there. So, because of this transmission line, there is a change in the S parameter. So, complete S parameter has a different behavior, and how you will get, there is a shifting because of the shift in the reference plane. So, we will just see that how the reference plane here is shifted. So, this is a S parameter of a 2-port network. This is A1 means already A1 and B1 we already know. Now, we are going to shift this A1 B1 to A1 dash and B1 dash. So, you can write a Bk, that is a reflected signal Bk dash, which is equal to Bk e raised to minus j Bk into xk. So, here why it is a minus, because we are travelling on the same direction back. That is why it is a e raised to minus j beta k x k equal to bk into e raised to minus j theta k, where bk x k is equal to theta k. Now for incident voltage, it is we are traveling on the opposite direction, means A1 dash is in opposite direction of A1, that is why there is a plus sign. So your AL dash is equal to AL e raised to j beta L into XL, where theta L is equal to beta L into XL. Because it is considered the lossless line, here mention beta L. If it is not lossless, you should consider it as a gamma L. So the updated S parameter, which is a SKL dash, which is equal to BK dash by AL dash, equal to BK. So we need to write the same, BK e raised to minus j theta k by AL e raised to j theta L. So this is a already available S parameter, that is a SKL, and what is the difference, e raised to minus j theta k plus theta L. So there is a phase correction. If your transmission line is a lossless, then there are a phase correction, but phase is also important. And you can also mention the same thing in terms of matrix. So the relation in terms of matrix, you can write e raised to minus j theta 1 if it is an n port, then e raised to minus j theta n, there is a S parameter of the actual device, and then there is a on other side there is a change in the reference plane, e raised to minus j theta 1 to theta n. There is a only change in the phase, there is a magnitude will remain same. So for S parameter, another important two aspect, that is the properties of S parameter is also important. So two basic property of S parameter is one is a reciprocity and another is a lossless network. So if your Sij is equal to Sji, you can write it down, your network, two port network is a reciprocal. If your total power flowing out is equal to total power flowing in, then you can consider it as a lossless. So you can mention your lossless condition, which is epsilon n is equal to 1 to n Sn I Sn nj conjugate, which is equal to delta ij. So if you consider n is equal to 1, so when your I equal to j is equal to 1 and your port is n is equal to 2 port network. So first you will get that is S11 S11, because I is equal to j is equal to 1, S11 conjugate plus then n is equal to 2. So S21 conjugate, which is equal to 1, because n is equal to 2. So you will get S11 square plus S21 square is equal to 1. So this is one condition. Similarly, if you consider I is not equal to j, your S22 is equal to S11, then your total power flowing out is equal to total power flowing in, and your network is a lossless. So by seeing the S parameter itself, you can identify that your network is a reciprocal or lossless, and it is very important in a RF circuit design to find out that your network is lossless or reciprocal. Now we will discuss about the Smith chart. We will consider discussing the Smith chart in the upcoming next lecture. So up to now we already have covered the transmission line and network parameters, which is important for the RF transceiver design, and means RF transmitter and receiver design. When you are designing at high frequency, you need to consider the effect of the transmission line and network parameters, that is the S parameter, which is very important for the measurement and while designing any active components at RF circuit also. So we will discuss about the Smith chart and impedance matching more in detail in the next class. Thank you.